can think that how quantum computing can help you. So there are other problems as well, even before I start the session. So let me go a little bit even outside the syllabus, just to clarify certain things based on the questionnaires. So broadly, those like, yeah, yes, sir.
Yeah, we are good to go. YouTube is also live now, so you can cover this part also as part of your lecture. So we'll start the formal lecture now, right?
Okay, thanks. Okay,
Whatever
so
you are covering, you can cover as part of the lecture.
yeah,
Thank you.
sure. Thank you. Okay, good afternoon, everyone. So today I'll be covering certain things, especially yesterday where we were a bit fast because of the time constant, but today we'll start formally quantum computing, and you do not need to worry at all about the things that I do not understand this part or that part. But at the end of QT-00 and 01, that course that you are taking, you'll have a very good overview of the various aspects of the quantum technology and quantum computing as a whole. But there is a series of courses, QT1 to up to QT11, I believe there are 11 courses. And these courses will help you, those who are interested to go in depth, like deep tech dive into the quantum technology. So to appreciate these things, so before I start the things, and I was responding certain queries that were asked yesterday. I'll again come to these things, but before that, let us come to the syllabus that is mentioned by EICT. We'll be following the syllabus as well as some of the things which are not mentioned in the syllabus. We'll try to cover some of those as well to connect these terminologies that mentioned in the syllabus. So there is this QT-00 part. You can see two things are mentioned. That is the linear algebra and the probability theory. Okay, so these are important. As I yesterday also I told you, why linear algebra. This is the language of your quantum computing technology, and probability and statistics, because all the quantum information that we will process, they are probabilistic in nature. And tomorrow and next to tomorrow, I'll give a broad overview of the probability and statistics that are connected with the quantum computing, especially quantum measurement and data retrieved from the quantum computer part. And as well as I'll give some notion of what is quantum error, noise, decoherence, as well as the various mitigation techniques. I won't cover much on the correction techniques, but just a part of probability, I'll mention the terminologies associated. And you can see some physics topics are also here, Hamiltonian and Lagrangian mechanics. Those who face much difficulty in this part, I believe professors like Professor Aswat Babu and Jaikumar and Dr. Jaikumar, and there are other faculty, especially Professor Anil sir, as well as Bhaskar sir are there. So they will help you to understand much deeper in this physics oriented and communication part. EM theory is there, electromagnetic theory, because those who especially work on the free space communication, right? And quantum optics, especially. In fact, in the superconducting quantum computer, we'll see a lot of application of EM theory when you try to basically process your quantum information from artificial atom to the cryogenic, in the cryogenic chamber to retrieve in the ultimately ultimately when you retrieve the information out of your quantum computers, a lot of EM theory applications is there. So some overview of the EM theory for that. Then there is computer architecture part, those who are very new to the computational part, because some of the scholars and professors might be from the out of computer science domain. So they may feel this part helpful. They may get this part helpful for them to understand various computer architecture, how it works. So these parts are there. Then there is digital logic and circuit. So how the digital logics and circuits works, basically the AND gate, OR gate, NOT gate, various flip-flops. I got some questions from there. So you will get a overall overview of the digital logics as well. Then there is QT-01. It's a separate course, but in this particular 20-day series, Professor Pillai sir intelligently combined these two, QT-00 and 01. So in 01, actually, this is formally like quantum computing start course. 00 is like prerequisite. If somebody is like some completed some BTech or engineering, or in fact some of the science courses, they may not need 00 at all. They can directly start with 01. So here you see that various aspects of the quantum technologies that government of India is investing, especially the quantum material science, quantum sensing, quantum communication, and the quantum computing. And I believe sir will circulate the syllabus to all of you. So no need to worry. It will be available in the online portal. So then I highlighted some of the things. So I will cover these parts, especially linear algebra parts today and part of tomorrow. And also there is like some of the things like quantum states, wave function, although the name of the course is quantum technology, not physics. So you may not seem this course is like a or like oversimplified kind of thing. So not the detailed physics will be discussed here, but the physics that is required at least minimally to understand or to appreciate how the quantum computing works, especially the superposition principle, entanglement, those things, and the associated mathematics, especially the Hermitian operators, unitary operators, expectation value calculations problem. So these are part of the things, and I'll be covering in the next 2-3 days of some of these parts. Then there is slowly we'll go to the quantum computation part. Like some of the like scholars yesterday, they asked what is qubit, why it is very different from bits and all. So I'll answer this today as well, like what is qubit and why it is so different from classical bit. Yesterday, a little bit I covered, like from the mathematical part and hardware part as well. From the hardware part, Dr. Richa also showed, and me also tried to show about the how the information 0 and 1 is generated on a semiconductor device, and how KT0 and KT1 we refer to the artificial atoms or the ion trap technology or various quantum technologies. If it is, for example, a photonic quantum computer, you can assume the vertical polarization at KT0 and horizontal polarization or as a KT1 or vice versa, right? So we'll come to that part. Then there is a quantum sensing lecture part, some of the lectures. So this is like articulated as a 30 like 3 credit course, and the previous one also 3 credits, but we have merged both of them in this 40 hours lecture series. So some of the things will be highlighted, some of the notes will be shared to you, but we'll be covering ultimately the total syllabus. And there is the quantum communication part. Regarding notes, before start my lecture, so I'm sharing my website here. So if you go to my web page, and also I think it will be shared with, by Professor Pillai sir as well. So you can see directly there are two notes. One is linear algebra for quantum computing for beginners. This is a UG level material. Those are very new to linear algebra, and they need to understand how linear algebra can help to understand quantum computing, quantum operators, quantum gates, circuits, various other aspects. So this is a very beginners level tutorial, and I'm covering most of my class today and tomorrow from this tutorial, you can see. And those who are already experienced in mathematics and physics little bit, and they want to understand various quantum algorithms and the mathematics required to understand those algorithms, such as the Krylov subspace, the Arnold iterations, various eigen decomposition techniques and all. So this is a postgraduate level tutorial, PG level tutorial also for the same topics with a different versions, like based on the difficulty level I attached here. You can directly download from here. With this, let us start, and if you face any question, please feel free to ask me. Okay. So regarding reference material, again, let me share the yesterday I shared the reference material, but today again let me repeat it. So reference material regarding lecture 1 maybe, yeah. So this those who are not from the like those who are just very new to this subject, and only they try to understand the quantum computation part and quantum little bit of quantum information. So this is like a bible in quantum computation. So quantum computation and quantum information by Nelson and Chuang, right? So you can directly start with this book. Those who are interested much in the quantum information theory, quantum communication, security part, like how quantum computer can help you to secure information or decrypt informations and those related parts, especially quantum communication side. So they can directly start with the first one, quantum information by Mario Mota. And then those who are interested from they little bit want to understand the quantum mechanics. And this is a widely popular UG level quantum physics textbook, Introduction to Quantum Mechanics by Griffith. And there are some other books as well I have referred. For example, quantum mechanics that is described in terms of the linear algebra, especially those who might not appreciate various like Green's functions and other quantum physics topics, but they try to understand quantum mechanics to appreciate quantum computing, they can start the reference number 9. So if you ask me to refer only one book, so this is the book you can directly start, but there are other important good books, so you can look at those books as well. Okay. So maybe we can now just take 1 second. Okay. Okay, so let us start little bit formally, and then we'll go for very very differently with other topics based on your queries and all. So I prepared a roadmap, very informal roadmap. We'll start today introducing quantum computing from little bit from physics sides as well, and then I will just after completing this part, I'll show some of the technological roadmap, especially from IBM side, because I belong to IBM, so I have the roadmap from my company, but there are other roadmaps from other companies as well. So you can look back to all of them. So in our UG or in our schools, we studied things like Max Planck's quantum physics, right? The particles, how they describes the particles, and for the first time you have seen equations like E equals to. Okay, let me take little bit. E equals to h nu. These kinds of equations we have come across with the h bar equals to the Planck constant kind of thing. So and the discrete level of energy phenomena, right? And so and so forth. We started learning. Screen is not visible. Somebody just asking screen is not visible. Can someone confirm?
Visible, sir. Screen is visible.
Yeah. If somebody
please check. Yeah.
Please, if anyone face difficulty, please rejoin. Maybe it will solve the problem. Thanks. So we started with the Planck's hypothesis, like the description of energy in discrete levels, and in the school level physics book, right? And then onwards, we studied various effects that couldn't be described in the classical Newtonian mechanics, such as the Einstein's photoelectric effect, right? And then we saw various atomic models like Niels Bohr's atomic model. Then there were the above principles. There were several other models in quantum chemistry, and there were a lot of development of various particle discovery, especially the discovery of electron, proton, neutron. So, and in that timeline also there were the general theory of relativity came in 1950, which is a so in physics there are two important theories, and in 100 years they couldn't change, like they are fundamental. One is the quantum mechanics and one is the theory of relativity. So these two are fundamental in physics. Okay, so okay, there are intermediate mechanics also, so I'm not covering the physics part because it's a quantum computing course, but those who are interested, so if you see classical mechanics, right, like the Newtonian mechanics, so there are intermediate development, like the classical mechanics to the quantum mechanics, and there were two important mechanics inside. One is the Lagrangian mechanics, and one is the these Laplacian mechanics. Okay, so they were part in between from the transition from classical mechanics to the quantum mechanics part. So, and part of the things I think that is there mentioned in QT-00. Okay, so some experts will cover those aspects. Then this we also know about the wave particle duality, right? So by de Broglie we say, but the pronunciation it actually is the Broglie, but we normally prefer to call de Broglie in our own pronunciation. So in the wave particle duality, that particle has both behavior of both the mass as well as the frequency behavior or wave behavior in 1923. So all this part actually this before the discovery of this part up to say the wave particle duality, or up to you can consider up to like 2020, 1924, 1925, this kind of some tentative timeline. Those were the first phase of quantum mechanics. And till this part, till the introduction of the Schrodinger equation, that is the first statistical description of the statistical mechanical description of the quantum physics, as well as the matrix representation of the quantum physics. So that was a very like a revolution, and that's why people call it the first revolution of quantum computing, or first revolution of quantum physics or computing, you can say. First revolution of, I will say, quantum science and technology, QST. First revolution of quantum science and technology. So even the introduction of the Bose statistics, that's the Bose-Einstein condensate and those phenomena. And slowly, the things went very well until the discovery of the entanglement in 1935, where people have seen, okay, if there are two particles, they are the distance is very far, even if the distance is very far, but still there is some natural relation, okay, natural correlation between these two particles, A and B, such that if you measure B, you see the effect of A. You cannot actually factor the composite state of A and B. So what this particular entanglement says about, so there are a lot of physics and paradoxes, so I'm not going to that part, but today I'll show you mathematically how what entanglement means, okay, how we can interpret the entanglement from the mathematical part. So that is one important discovery. And in fact, the discovery was done by the Schrodinger, but it was actually the paper on the entanglement, first paper on the entanglement came based on a paradox called the EPR paradox. So Einstein-Podolsky-Rosenberg paradox. So there was a paradox before the discovery of entanglement. And even like 2 years back, probably you have seen that professors from MIT got a Nobel Prize on this theory, proof of the entanglement, right? So this is so important. Even the theory came in 1935, but still things are happening right now in the quantum technology era, right? And there are lots of development. So like what we call the modern quantum mechanics and all. So for example, the Heisenberg's uncertainty principle, matrix mechanics by Heisenberg, Max Born, Pascal Jordan, etc. And then there are a lot of development, scientific development, such as the quantum chromodynamics, quantum electrodynamics, right? Especially if you see the Feynman's work, right? So many works in the quantum electrodynamics, and he got Nobel Prize in 1965, right? So so it was a like strategic development and the scientific development until Feynman showed that it is very difficult to simulate physics, especially quantum physics, the quantum system on a classical computer, because if you want to simulate quantum mechanical system efficiently, you better need a quantum computer. That's what the first theoretical proposition that he gave in a lecture. And okay, I'm getting some question. Okay, fine. Then after his introduction of quantum like computing, right, model, first computation model was proposed by Deutsch. And whoever opened the book Quantum Computing or has taken any like any workshop or quantum conference wherever, they have seen this kind of model, like Deutsch model. So the first theoretical model to the first quantum computing model, theoretical model that is coined by Deutsch, and then later realized that, okay, there are some problems which actually we can better solve on a quantum computer. So the first introduction of the quantum computer, and then Source first time has shown that finding the periodicity of a number or of a function and is much faster, even it is in polynomial speed, which is classically exponentially hard, means very hard. So how much hard, maybe we can discuss it in some algorithm class, but not now. So he has shown there is a exponential speed of in finding periodicity and factoring numbers, right? And so and after that, Grovers also find that, okay, if there is an unstructured array of numbers, say there are numbers like 1, 5, 10, then 6, then 8, then 2, and so on. You can find which is the minimum or maximum number, right? Much faster on a quantum computer. Like classically, it takes n step to solve, but quantum mechanically, it will take square root n complexity, square order of. Okay. So there are proofs and all those things. But until 2016, when IBM first time launched the first processor, quantum processor, and there are so many development by other companies like Google, Honeywell, and other companies as well in the last decade. And this decade, basically this decade, I can say, like in last 5, 6 years, 7 years. So people invented hardware based on the principle of quantum physics. Some of the hardware platform like Dr. Richa yesterday she showed. And from this point, before introduction of hardware, whatever algorithms we had in the quantum mechanical framework also, and most of the algorithm we say they are query complexity algorithms. Means there was no hardware, so resource measurement was not there in terms of practical applications. But when hardware is there and we actually try to solve the problem on the hardware, and we see various difficulty level, like how much error is there, what is the memory capacity, memory actually in terms of the classical I'm saying, but in quantum there is like coherence time and other things. So there are many difficulties, how many quantum gates you need to actually cooperate with the coherence time and all. So we come with a concept called gate complexity or resource complexity. Okay. So there is a roadmap here. Just I'm trying to connect the physics, computing, and then the technology part. So let me show that part just to help you the roadmap. So yesterday someone asked me to show the roadmap. So this is a roadmap from IBM. You can see like there are certain things. Like yesterday I showed. Just allow me seconds. I was scrolling. Okay. So there are like development roadmap, a quantum plus high performance computer integration, but let us only stick to this part. So in 2016 to 19, we had processor like early processor with 5 qubit, right? And slowly there are certain things like control mechanism, how many gates I can operate, what is quantum gate and all, I'll come. So right now in 2024, if you can see, we have the Heron processor. Here it is written 133 qubit, but practically we have in fact 156 qubit processor. Okay, and we have targeted to reach to 1 billion qubit by 2033. And in 2026, 2027, we target for fault like the quantum advantage kind of demonstration, because till now we have 100 qubit region where we demonstrate the utility applications. I will share the roadmap as well for the details. So how we basically developed from 5 qubit to 27 qubit, then 127 qubit, 133 onwards, and what are the number of gates. So now you can say, can I increase the number of gates? Yes, you can increase, but the overall number of gates that you apply should obey the quantum coherence time. Otherwise, you will get some answers which is not practically useful. Okay. So this detailed roadmap I'll share to Professor Pillai sir as well. So to show you, or you can see various roadmaps technologically, like what will be the processor, what will be the characteristics of the processor, what is the gate capability, what is the coherence time, and all details are in the technology sheet. Okay. Fine. Now let us come back to the theory class again, and slowly I'll go very slow, such that because some of the concept might seem a bit complex to those who are not from the physics side. So let me cover those things very slowly, and ultimately I'll come to the computing part, where even if you miss some of the physics things or you don't understand, you can go back to the notes, but you can start from that point as well. So you do not need to worry at all. Okay, so let me check some questions. What are the advantage of quantum computer over conventional PCs? Okay, yesterday slides you may look back. So I have discussed this part, especially the supercomputer versus quantum computer examples are there, applications are there. What is mean by coherence time? Okay, I'll come. Okay, so I said that in order to understand quantum computing, we are relying on the principle of quantum physics, right? And quantum physics, I won't go much detail from the physics side, but as a mathematician, or you can say like from the mathematical point of view, what are the interesting things or important things that we need to consider in order to understand the quantum computing, right? So mainly, at least we need to understand the various postulates or the assumptions. Okay, what are the assumptions are there in the quantum physics that is required to basically validate the quantum computational framework, right? So what quantum mechanics tells us is that something that describes the any phenomena of matter or any physical phenomena is a wave function, right? And wave function, when I say wave function, I represent like psi, or you can represent as fx comma t, is a function of space and time, right? When I will represent it as a vector, not as a function, so basically I will write it as a ket notation. This is called ket psi. Okay, those who are new to the notation, so I'll also define the notations as well. So this is a vector notation, right? Now you can immediately ask me, okay, physics tells about function, and you are saying about vector. Then why shall you go from function to vector? So function is like if you take a continuous functions, right? So there are infinity number of points. You cannot store it, right, on a digital computer or any computer. So you need infinite resources. That's why we do discretizations, right? And once you discretize these functions, say for example, if your function is x versus fx, okay, and you take some value, say f0, f1, f2 to n number of points or n minus 1 number of points, then you can write the vector representation of the function, in fact. So that will be some f vector, and that is just the string f0, f1 to up to fn minus 1, right? Just uh, to store the information on a digital computer, or for which is easy for processing or efficient for processing. Now you can ask me, am I not losing information? Of course you are losing information by discretization. Okay, but there are mathematical tools which can help you to reconstruct maximally using interpolation and other theorem. Okay, so the first one is that anything that you want to represent, any physical phenomena, the best description is by a wave function. And what the wave function has to do, there are certain rules or the postulates. Okay, and we'll come back to each and every postulates from a mathematical way, easier way. Okay, so wave functions that contains all the information about a physical system. A physical system can be any system, right? It can be like throwing a ball in the air, with a physics example, or it can be our brain, our cardiovascular system is a system, right? It can be any telecommunication system, your mobile phone, radar, anything, right? So, and I will take two example here, two very distinct example. One is the plane wave, and one is the Gaussian wave packet. So if you see the Gaussian wave packet looks like this, just it's a plot. I did this plot in MATLAB or any software you can do. So this Gaussian plot, you can see this most of the energy of the plot is concentrated within a small position dx, right? So if you define this part as x and this is as fx, right? Fx means psi x here, wave function. Most of the energy content of the signal is concentrated within a very small region of the x, delta x, right? So that's why it is concentrated over it is defined within a small region of x. And if I say what is the probability of getting this of these wave functions within this region, say here to here, and it is, you can say 99% or something, right? So it is the integration of energy, so psi square x dx from this point, say x1 to x2. So this is the area, right? This is the area which is the energy part here, right? But if I say that if it is a plane wave, it looks like this. Now you can see it is not concentrated over the x, but it is distributed over x, right? So here you can see that it is not localized in X. But if you take the Fourier transform here, I'm not telling you to do right now. You'll see in the frequency domain, if you plot frequency versus the wave function psi of X, say for example, it will be psi of F then, right? Then you will see that if it is a sinusoidal signal, you will get some peaks like this, right? That means it is concentrated over the frequency, not in the time, right? So here, if I define this wave function, if it is sinusoidal, say e to the power I omega, so here it is written, right? E to the power I kx minus omega t, say minus omega t. Now, if I represent in the time domain versus the frequency domain. So this omega, if you convert to omega equals to 2 pi f, right? The frequency part. Now you see that when you have uncertainty in X, so you have you cannot represent these functions localized in X, but it is localized in F, not in X, right? So there is an uncertainty in X and F, and that's how. But again, in the Gaussian wave packet, you have certainty in X. But if you do Fourier transform here, convert the domain to some F domain, you will see that it is spread out. Okay, it is spreaded out. So those things are related with the wave function. These are various behavior, uncertainty relations and all. So I'm not covering those aspects, but they are related phenomena. Okay. Now, let us try to cover the operator picture. I'll just take 10-15 minutes to cover the quantum physics, and I'll again come back to the quantum computing. So those who do not prefer physics, just bear with me for 10 minutes. Okay. Okay. So now this is another important thing. So from here, you understood that there are quantities which are localized in one domain A, but may not be localized in another domain B. That means there might be uncertainty of the same phenomena into different domains, right? And that's why there is a theorem called Heisenberg uncertainty principle, right? And I'll define this mathematically, don't worry. Now in physics, there is another important thing. So this is basically postulate number one. You can represent any information using a wave function description, okay? Now the second postulate is related to something that is, it is telling if you have a wave function and you are saying, or I am saying, that all information is embedded within the wave function. Now, how can I retrieve a particular information? Suppose there is a wave function and I want to estimate the position or the momentum or the energy, right, of the physical phenomena. Then how do I do that? Then it is said that for every physical quantity or every wave function, there is an associated operator A or a matrix A. And if you apply that matrix on the operator, right, you basically get some eigenvalue of the operator, right? Then if you want to get the eigenvalue of the operator, so this has to be Hermitian operator, right? This lambda is the observed quantity, A is observable matrix, right? So now you can ask me why it is a Hermitian operator, why it is a Hermitian matrix, right? So in algebra, we studied that the eigenvalue of the Hermitian matrix are real, right? Are real quantities, right? And all the physical quantities in physicists always prefer for real quantities or actual, that is not imaginary or something, not this thing. So for example, the energy or the momentum, right? Momentum, or in fact, the position, right? So these all are the real quantity. That means some watt of energy, some particular value of momentum, some particular meter of positions, right? So if you want to find the, for example, if you want to find the position of some particle, right, in classical physics, right? So then position becomes your eigenvalue of some operator x hat, right? If I apply that operator on the wave function, I should get the eigenvalue as the desired quantity of that wave function. So this is basically eigenvalue equation, right? I'll come this in details later. Okay, don't worry. So now for every physical quantity, that means if I want to estimate certain quantity of a wave function, I should find what is its equivalent operator that should operate on the wave function and return the eigenvalue as my desired quantity. Okay. For example, if it is a position operator, it is x hat is the operator. If I apply x hat on the wave function, I'll get x back. For example, momentum. The definition of momentum is h bar k. K is the wave number. Okay. So how to get this wave number? In fact, this is the eigenvalue of the operator I h bar del x. If you apply this I h bar del x on the wave function, you will be getting back this h bar k. So for every quantity like energy, frequency, there is a corresponding operator, there is a corresponding eigenvalues. Eigenvalues are the things which we can measure on the quantum system and we can see after the measurement, right? But there is an associated operator that I need to perform on the wave function. So this is one important postulate. Now, when we come back from physics to computing part, this wave function will become circuit notation will be your psi will become ket psi because you need to discretize it and what will be the component and everything I'll discuss. And this a hat, which I am differential equation I have shown here, right? This a hat in circuit or in mathematics, it will be a matrix basically. Okay? And physicists prefer Hermitian matrices because they want real quantities. But if you have complex quantities like phase and etc., this Hermitian condition may be removed. Okay, only some metrics. Okay. So somebody asks what this equation. Okay, this equation one is basically the equation of a Gaussian wave packets basically. Wave packet, and this is a plane wave function definition. You do not need to just consider these things. Just this is some wave function. It can be very arbitrary as well. Now, I was saying the operator picture. This is important because when you will design various quantum algorithms and quantum algorithm-based solution, you need to find, okay, I have some problem. Then if you have some problem, you need to think, okay, what is the relevant wave function for your problem, at least the quantum state for your problem. Then if you are interested to find certain parameters or certain observable out of your problem, then you need to think, okay, what should be my corresponding operator, mathematical operator. I am right now telling you operator as a matrix, say A. Later, I'll show what is the quantum circuit for A. Okay, what is the circuit for A? Once you design the quantum circuit for A, then you have a matrix representation of A. If you can apply that A on the wave function and you do the quantum measurement at the circuit, you will get back your desired result. So I'm relating the physics to the computing part as well. So for example, the position operator X has the operator X hat. If you apply X hat on the wave function, so X time psi X, so it is directly X times the psi X. So it is giving you X as the eigenvalue. This is trivial one. Now let's take this momentum example. I am defining the momentum operator in this differential equation form. Now let's take a plane wave e to the power I kx minus omega t. K is the wave number, x is position, omega is the angular frequency, and t is the time. Okay. So if you just apply the momentum operator here, so it's a simple derivative, right? A partial derivative with respect to x. So I h bar constant, a is constant outside, and then this part. So this part will be simple derivative. If you do, you can see that I k this part coming outside, and the next part you can do the derivative will c to the power I kx minus omega t. Altogether, it is h bar k a e to the power I kx minus omega t. So this part again sigma. So you are getting h bar k psi xt. So h bar k is the eigenvalue, right? Because eigenvalue equation is what? Ax equals to lambda x, right? So Ax equals to lambda x means there is a vector, non-zero vector, for which if you perform a matrix or apply a matrix, you get a scalar quantity, like scaling of this vector, not changing the direction, right? Lambda time x. I'll come later in detailed description of what eigenvalues and those details things. For now, the desired quantity h bar k is the momentum p, not p hat. Okay, so this is the eigenvalue of the operator p hat. Now, similarly, you can compute the Hamiltonian operator. So Hamiltonian operator is defined at I h bar del del t. It gives you the energy quantity back, right? So simply again you do the derivative of the plane wave with del del t. You will get back. You will get to see that it is h bar omega, and we know that E equals to h bar omega. This is coming from the Planck's equations, right? H bar is basically h by 2 pi. So you cancel out the 2 pi thing, and you will be getting to know that this is equals to h nu, right? So this is related with the operator picture to the actual quantum postulates that came in the quantum physics, right? Now, similarly, there are lots of expression, but I gave the notes. I'm not covering those parts in detail, but now let us go back to the bit on the quantum computing sides again. So this ket notation is basically is a set of string of numbers x0, x1 to xn minus 1. This is called the ket notation, ketx. Okay, this is simply a column vector. Okay, this is bra x. Bra x is a row vector basically. Row vector, right? This is a row vector and this is a column vector. So the dimension and the elements x0, x1, x2 to x minus n, these are complex quantities. So you can say it's a complex column vector. Okay, complex column vector because all these xi are complex numbers. Okay, so the dimension of this can be n cross 1. This also 1 cross n, right? So I said these are vectors, right? And so they should follow the vector space properties, right? So there is a lot of properties and all I give in the notes. I'm not covering those part in detail, but in general, you know, there are two properties you need to follow. One is the scalar multiplication property. And second is the vector addition property. Vector addition property. These two property it has to satisfy. Okay, and there are certain rules for the vector space and all. So those who might not be familiar in this part, they can directly go back to my notes for the details. But what is important is that certain things, especially if you have two vectors, say kx, one quantum state, for example, and another quantum state is ket y. Okay, and they follow their the vector space properties, right? Then what you can do, you can always linearly add them. That is alpha times kx plus beta times ket y, and that is also another valid quantum state ket psi. Okay, you can represent as ket z, right? So what I am saying, this is very simple, like vector addition principle. If you have a vector x, say x vector, and if you have a vector y, right? In our school we have seen this. Then you can add these two vectors using parallelogram law, right? And this will be your r vector is basically x vector plus y vector, right? So you can take the scale of a, in fact, alpha times some x. This is alpha x, and this is beta time y, right? Still you can add them. You can add them. So you can check how the addition will be. Probably this is the addition, right? So this is your the vector ket psi. And this is exactly what is called the quantum superposition principle. Now there is additional condition on A, alpha, and beta, because if X, this ket psi has to be a valid quantum state. What the quantum state is saying is that the square of this norm of this vector ket psi should be equals to 1. Okay, any valid quantum state has a norm 1, and that is coming from the probability law. I'll come tomorrow what is the probability associated with these things and all the same phenomena with the probability definitions and all. So that means the condition is alpha square plus beta square equals to 1. Then this same vector addition principle works for the quantum superposition. Okay. So there are some more thing like what is called the inner product, what is called the completeness relation. So you can look in this thing. So there is two product we need to know if you want to do dot product of x and y basically, right? So this is the sum of x I star y over all I. So that is component wise multiplication and then add all numbers. So let me give one example for clarity. Say you have two vectors, 1, 2, 3, and 4, 5, 6, for example, 4, 5, 6. So the inner product is you multiply each and every element and then add. So 1 times 4 is 4, plus 2 times 5 is 10, plus 3 times 6 is 18. So it is 10, 28 plus 32, right? So 32 is the inner product of these two vectors. Say it is vector A and this is a vector B, right? The inner product of A and B is 32. There is some something more that is called the outer product of two vectors. So outer product is written as this way. So I have shown the inner product in this way, this bracket notation, and this bracket notation is basically what I am doing. Actually, this notation is actually is your this times this, right? But here it is this x, that is a column vector times the row vector. So your column vectors is what is the column vector size? Your column vector is 1 cross n dimension, right? And times n cross 1. So what will be the overall dimension? N cross n. So column vector times row vector is basically a matrix. So if you do the outer product of two vectors, you will get a matrix. So x, although these are very basic concept, but I thought might be useful. So I'm adding this here, x, y outer product. So outer product is basically a matrix, right? And this is related to expectation calculation, in fact. Expectation calculation. So sometimes later I'll come back again. So if you want to calculate the expectation of an operator, because there might be quantum uncertainty coming from the noise and other things. So if you want to calculate, suppose there is an operator A, and you want to calculate the expectation psi A, psi star, or some other psi, it may be. So we write the representation as this way, right? So this is called the expectation representation. So what I am doing, matrix times the vector, you need to first do matrix times vector. So vector is a column vector, so it is n cross 1. Matrix is basically cross n. So, and then this is 1 cross n, right? So basically this n cross n, it will be n cross 1 again, right? So n cross 1 again, and then it will be 1 cross n. So it will be 1 cross 1. That means it will give you a scalar quantity, right? Did I make a mistake here? Let me check. So it will be n cross 1 and it will be 1 cross n. So 1 out, it will be n cross n. Okay. So because I denoted the column vector as n cross 1, right? Here you can see. So so three notations we need to know. One is the inner product, one is the outer product, one is the expectation calculations, right? And this completeness relation will prove it using certain other things, right? For example, okay, I'll come this when I'll define what is quantum operators and all. Okay, so this is the definition of your inner product, like component wise multiplication and then addition. Okay, and norm is basically the square root of the inner product. Okay, and the linear combination of basis vectors. Okay, so this is important. So, so basically, yesterday we saw that any vector, if you want to represent, right? Say, for example, a vector is R, right? You want to represent on a two-dimensional system. So you need a coordinate system X and Y, right? Say, and those coordinate system are orthonormal to each other, 90 degree, right? Say, for example, this is E1 and this is E2. This is your X-axis. This is your Y-axis, and you can represent this R as alpha amount of this this E1 and beta amount of this E2, right? And the combination of R is alpha E1 plus beta E2. So this is the represent of any arbitrary vector you can represent in the certain basis. So any information you want to represent, you need a basis system. For example, in a classical computer, if you want to represent your information, you need the set of bit string zeros and one, right? Their bit string itself carries the information. But in quantum, when you try to represent the information, you represent in terms of ket0 and ket1. And yesterday I showed that ket0 and ket1 are orthonormal basis vectors. Often they are called computational basis vectors. And any quantum state K psi is a basically linear superposition of this 0 and 1. Now, if you increase this number of bases, there are say n number of bases. So it is a linear combination of those n number of bases, right? So you can represent any quantum state in a some coefficient times a basis vector and sum of all those basis vectors, right? Now, again, the condition is that all those basis vector that has to be like if you multiply these two vectors, it is 1, right? But if there is n number of vectors, so all the individual vectors, if you multiply, the vector, okay, let me explain this part in a much concrete way. Suppose this vector is 0 vector, okay? So 0 vector is what? 0 vector is your 1, 0, right? So if I multiply 0 with 0, what I will get? 0 with 0 means 1, 0 times 1, 0, right? So it will give me 1, right? So the inner product between this between the same basis vector is 1. But if you multiply between 0 and 1, say, what you'll get? You'll be getting 0 is basically 1, 0, and 1 is basically 0, 1. It is 0, right? So two different orthonormal bases is giving you 0, and two same orthonormal bases is giving you 1. That means if there is Eij, right, it will give you so basically delta Ij, right? So if I equals to j, you'll be getting 1. If I not equals to j, you'll be getting 0, right? If you multiply two things, Eij times Eij dot product, okay? So if you prepare a matrix with this kind, say I comma j position, all these diagonal positions will be 1 and all the other positions will be 0, right? So as a whole, if you multiply these things, what you will be getting is that the sum of all those basis vectors, right, outer product will be equals to the identity matrix, right? And this is called the completeness relation in quantum operator picture of the quantum mechanics. Okay? Now, this gives one important thing. I will come this part. Okay. So again, let me come to the postulates formally, and I'll come here again. Okay. Okay. So in quantum physics, we have seen all information contained in a wave function. In quantum computing, we'll say that it is just a column vector, complex column vector with normalizations. That means that the inner product of the quantum state, any quantum state we prepare as a vector, the dot product with itself will be 1. This is the first quantum postulate. Okay. Second, any operator we perform on a wave quantum state, it should return the eigenvalue of the corresponding operator. And that eigenvalue is the desired. If we measure that eigenvalue repeatedly, okay, we get the desired quantity. Okay. Now, if you want to get this desired quantity as a real quantity, you should have a that observable matrix or the operator Hermitian. Okay, Hermitian matrix, because of the eigenvalues of the Hermitian matrix will be real. And if you measure repeatedly in a quantum system, you'll get the real quantity back. So this is related to your quantum postulate 2. Then third is that if you do the measurement on a quantum state, right? So we have this expression is difficult to understand. Okay, let me clearly show these things here. Now this is an arbitrary quantum state, K psi. And I said, okay, it has some arbitrary presentation, but I can always write it to the computational basis 0 and 1 as alpha K0 plus beta K1, right? Now, when I say you do measurement of the quantum state, in order to tell me whether it is head or tail, whether it is 1 or 0. In quantum mechanics, you cannot definitely say, okay, this is 0 or this is 1, because any quantum arbitrary quantum state is a superposition of the basis states 0 and 1, right? So what I have to do? I have to do repeated measurement, and I can say probabilistically, I can say, okay, the probability of 0 is this much and the probability of 1 is this much out of n times experiment, right? Now, probabilistically, I can define, okay, the probability of the quantum state psi in 0 is, suppose I repeat n times experiment and I get it n1 times and I get n2 times. So I say the probability of the state 0 is n1 by n times, and the probability of state 1 is n2 times by n. This is the probability definition. Now, linear algebra also give you a freedom to quantify this. And that is exactly what is called the quantum measurement operator. Okay, how to do that? So psi is alpha times ket 0 plus beta times ket 1, right? And we just learned what is inner product, right? Now, if you do the inner product of psi with 0, what you will be getting? Alpha 0, 0 plus beta 0, 1. Sorry, 1, 0, right? Or I mean, it's whatever way you want to write, that's okay. So this 0, 0 times 0 dot product is 1. So alpha times 1. And 0 dot product with 1 is just, we have proven it is 0. So beta times 0. So it is giving you alpha. So that means if I do a mathematical projection here, I get this is as alpha, right? This is at alpha, right? And it's a complex quantity. If you take the square or norm, you will get the actual value of this, right? So if you mathematically take the projection of this vector in the x-axis or the ket 0, you'll get the probability of this state 0. So normally, trivially, we said the probability, we can see that probability of ket 0 is alpha and probability of 1 is beta, that we can trivially say, but mathematically also we can show that if you do a projection on the basis 0, we get alpha. And if you do a projection on 1, you will be getting beta, right? And if you take the square, so basically then the actual value will be getting as alpha square and beta square, that is the probability. These are actually called amplitudes. And these are called probability values. Probability values of the state 0, psi in 0 state and 1 state. So if you have now if you see, if you have a quantum system which is state psi and you have a measurement basis, now I have shown everything in terms of 0 and 1 basis, 2-dimensional case, but this is not sufficient to represent my information. Okay, I said information. Okay, let me define information as well here. Although normally I take this in the information theory session, quantum information theory, but let me little bit introduce here. Sometime later somebody or I'll take this part in much detail. So information in classically you have 0 and 1, that's all. And if you send some information place A to B, right? So what it can change, only 0 can become 1 or 1 can become 0, that is the only error, right? Error can be either 0 or 1, right? If you have a bit string, say 001, you have sent and you have received say 0010. So there is a mismatch of the information. So all this is about the classical information. But when I say quantum information, ket 0 and ket 1, there is more about other than this ket 0 and ket 1, because you are representing your quantum phenomena in quantum state ket psi, and that is equals to alpha ket 0 plus beta ket 1. So there is 0, 1, alpha and beta. 4 quantities are there, right? So you can represent more than the 0 and 1. In fact, it is a theoretically it's an infinity combination of 0 and 1, right? But there is a hardware limit, physical limit of this information. Now if I want to if I have a 2-dimensional case, so basically 0 and 1, but if I have say 2-qubit case, for example 00, 01, 10 and 11, with only 2 bits I can represent 4 quantum basis states, right? So if you have b bits, how many quantum state you can create? 2 to the power b quantum states you can create. Because earlier with only b bits you could classically represent only b numbers, For example, in the hello message, if there are some numbers, say 10101010, this is your, suppose this is the hello message. So how many bits are there? 4 and 4, 8 bits, right? And that's all. You couldn't do much. So you have taken 8 classical bits to represent these 8-bit string representations. But now, if you have only 3 quantum bits together, now you can create state from 000 to 111, right? So you are only you have only 3 computational basis states, say 00, ket0, ket0, and ket0, right? 3 state. You can combine them and create how many possibilities? 2 to the power 3 possibilities, 8 possibilities, right? But difficulty is that now the quantum state you are preparing, which is a combination of all these 8 basis states, that is, say, A0 000 plus A1 001, so on, plus A7 111, right? This is the now state, and none of the states are right now deterministic. All states are probabilistic now, and they have an associated probability A0, A1, A2 to A3, and A4, so on to A7. Okay, so now your information becomes probabilistic in nature, but you have a better expansion space, right? That's why your Hilbert space is so large now. N bits you can represent in 2 to the power n computational basis states. You can encode your information here. You can encode your information here. You earlier you had error only 0 and 1, right? But here you can create ket 0, ket 1. In fact, minus ket 0, minus ket 1. This is called the phase error in quantum information, which is not there in classical computing, right? So there are so many things in quantum information as well. But so far, what we need to understand is that your quantum state is no more deterministic, it's probabilistic, and it has certain probability with the associated basis states 000001111 and so on. Now every time if you do measurement, likewise the 2 qubit settings, like I could measure in 0 and 1. Similarly, if there is a n dimensional setting, like 2 to the power n basis states, so these are all 90 degree. I cannot draw like this. Suppose this is a 4-dimensional space with say 0001, 10 and 11. Suppose these are 490-degree apart each other, suppose in space, right? And you have a quantum state psi here. Now if you measure it repeatedly on this basis, this basis, this basis, and this basis, you get the probability, right? So effectively what you need to do? Effectively, we need to do the inner product, right? Inner product of the wave function with the computational basis, that is denoted as phi n. Phi n can be 00 computational basis to 11 computational basis. It can be, in fact, for a more bits, say it be 000 to 111. In fact, b number of bits, all 0 to all 1, right? Many ones, many 0 to many 1. But the good part is that now using superposition principle, you can create some n bits to 2 to the power n possible states. That's a big space you can create using the superposition principle, right? Now, okay, this part is fine. So now if you do the inner product, that is you do the inner product of these wave functions to a particular basis, you get the probability of that particular wave function in that particular basis, right? So there are associated probability theory, how you can enhance the probability of a given state using certain estimation theory problem, and also that is not part of this class, but somebody will take in future session. So I'm stopping here for 2 minutes and 2-3 minutes, and I'll come back again with the famous Schrodinger equation, and I'll introduce qubit, associated operators, and everything after that. Okay. So I'm stopping here, and if you have any question, please feel free to write it in the chat. There is a good doubt. Somebody is asking whether these probability amplitudes are part of the states or not. Okay. The answer is how you represent information. So there are many books writes in different way, but let me explain this part. Suppose your quantum state psi, right? You are representing as alpha ket 0. It's a very simple way, plus beta ket 1, right? Later, in fact, when we'll have bigger states, we will represent this ket psi as equivalently as a vector alpha comma beta. We'll discard this alpha beta because this is understood that alpha beta means alpha times ket 0 plus beta times 1. In fact, we will represent this probability amplitudes as a vector for representing quantum state, right? So this will elaborately cover in the quantum information theory part. When you do not need explicit representation of the states, you can directly encode the probability amplitudes, basically not the probability values, the amplitudes as a matrix, basically as an element of the vectors, right? And then this will be your representation of the state, right? So I hope this makes clear. So when you have a bigger space, say for example, ket psi, I can represent as A0 ket 000 to A7 111. In fact, this is equivalent to, you can write it as A0 to A7 this way. Now this becomes the coefficient of your state vectors. Any other doubt? Let me check. And we'll start exactly at 420 again. That is an excellent question. Could you explain adding two numbers 2 plus 3 using qubits? Okay, great question. Well, one sentence, and I'll explain it much detailed, but the direct answer is when I was just submitting my PhD thesis, I was completing, I realized that addition is not a valid quantum operation. Okay, and I'll show you why it is not a valid quantum operation, right? Okay, let us start maybe. So superposition is just okay. Somebody is saying voice is not coming. Can somebody else just ping that voice is audible or not? Yeah, thanks. Yeah. So superpositions that we have seen is it's simply coming from the like addition of two vectors, right? But there is only additional condition on this coefficient C1 and C2 and so forth, right? So superpositions part is not that difficult, but it is one of the like most important quantum phenomena, I would say, right? So that if you know to, okay, let me explain this part on the right side, and I'll pick up the question why addition is not a valid operations, right? So um, so any quantum state, say psi, right, that you can represent, say alpha ket0 plus beta ket1, and any other state, say phi, that is say gamma delta 0 plus delta ket1. This is the state, and how it looks like. So it looks like this. This is your ket psi, and suppose this is your ket phi. If these two are the quantum state and these two are the valid quantum state, your superposition theorem says you can always add these two states in superposition, that there is some combination of this psi and there is some combination of this phi, linear combinations phi, and you get some other state. Say this state, I'll say this state as say x, for example, right? I prepare some state x, and this is also a valid quantum state. Valid quantum state. And this is a most powerful theory in quantum computing. Even not entanglement, I would say. All the computation power is coming from this theorem. If you have two valid quantum state, and later I'll show if you do the composite quantum system preparation just after this session, okay, just after this point, and you'll see how much powerful it is, right? If you have two valid quantum states, psi and phi, and there is a combination C1 times the vector psi and the C2 times the vector phi, and whatever you will, that is also another valid quantum state, right? Now, there is a question whether I can add two numbers or not. Okay. So initially what I have said, which is related to postulate number one, assumption number one in quantum theory, right? What it is saying is that it is in fact nothing quantum here. It is some obvious things, right? Say, what is the thing? Is that my for an isolated quantum system, if it is a state psi, right? And suppose it can be expanded, or it can be represented into basis states, ket0 and ket1. Suppose these are two basis states for this psi, right? So there is of course a probability to the state 0, and of course there is some probability to the state 1 for this wave function psi, right? Is there any condition on constants for? Of course, there is a condition for the constant, and the condition is okay. I'm coming to the condition. The condition is sum of all the coefficients square equals to 1. This is the condition for your composite quantum system, right? Your overall representation of the wave function. Wherever here it is alpha square plus beta square equals to 1. Here it is delta square plus gamma square plus delta square equals to 1. Here it is C1 square plus C2 square equals to 1. In fact, right? So this is the condition, and this is one important condition, and this is related with our physical intuition. In fact, if the wave function has two possibilities, like there is probability associated with 0 and probability associated with 1, then the overall probability should be equals to the probability, overall probability of this wave function equals to should be equals to 1. So this is directly coming from the probability theory, very simply. Now let us revisit these things from calculus, right? So what it is saying, suppose this is your functional space, right? And suppose this is your arbitrary wave function, ket psi, not vector notation, it's a some psi. So calculus, so it's a some function psi of x, say, and this is a function x versus psi x. So of course there should be some limit, right, for the physical phenomena. Some physical phenomena cannot be infinite, right? There is a limit to that, right? I can always limit it. And if I say the limit is between x1 to x2, right? What it is saying? the quantum theory is saying that the area under this curve, right? In fact, the area under the square of this curve. Okay, so if it is psi square x, in fact, then integration of the psi square x dx between the point x1 and x2 should be equals to 1. And that gives you the probability, overall probability. Here x0, x1 is your ket0, here x2 is your ket1, and you have taken two discrete points, that is alpha and beta. But in functional space, it can be continuous, and there might be infinite number of points. So integration x1 to x2, psi square x dx equals to 1, right? So now this condition I told you from the probability, from the calculus. Now I am telling you from algebra. The same phenomena. What algebra says is that, suppose you have a quantum state psi, right? And you are saying, can I add two numbers, say 2 plus 3, right? Suppose if 2 is a quantum state psi 1, right? I am just I cannot always write in this way, that scalar in the vector form or something like that. Suppose 2 is a person, and 3 is another person, or 2 is a quantum mechanical phenomenon, and 3 is another quantum mechanical phenomena, and I want to add them, right? Psi 1 times psi 2, psi 1 plus psi 2, right? These are two quantum mechanical phenomena. Now, what quantum mechanics tells us, I cannot simply add them. Why I cannot simply add them? Because what I can always have, I can always evolve over time. What Schrodinger's equation says just after this, I can always evolve over time. If it is at time equals to t0, I can go at time equals to t1, for example, right? Now, wherever I do, suppose I forcefully do the addition and I get something psi 3, okay? This is very arbitrary example. It has no relation with any textbook. I'm just trying to prove it. It is not a valid operation. Now, what quantum mechanics is telling me is that suppose suppose I get a evolved state, that is evolved state EV I am writing, and this has happened after certain operations here. I am writing as pops as my operations, or I can always write it as a matrix form. Say it is some B matrix, okay, which is operate on the initial state, say psi initial, right? Suppose this B is doing your addition operation, right? Or some operations, right? Now what I have to do is that I have to always check that the sum of the norm of this first one should be equals to 1, right? And norm of this psi init, this is evolve, init should be equals to 1, right? So I can always do that when and if and only if, right? So that means evolve state like EV psi EV, if I do the norm square, that means B star B, right? So it will be your psi init B star B psi init initial state. So what it is equivalent to x star B x, this equation. Just expanding this, squaring this. You just need to square left hand side and right hand side. What you will be getting? Some row vector times the matrix transpose times the matrix times the column vector, right? You are getting this. So if it is equals to 1, and this will be equals to 1 if and only if B star B equals to identity matrix. If and only if this condition is satisfied, then only it is equals to psi init square, right? And from quantum mechanics, I know this is equals to 1, and right hand side has to be equals to 1 to have a valid quantum state, right? Then the only condition is B star if B equals to I, and this condition is validated only if B is called a unitary matrix. Is a unitary matrix. That's why all quantum operation are unitary in nature. All quantum operation are unitary matrices, unitary in nature. It has to be validated. Otherwise, probability will fail. You'll get some different probability, maybe greater than 1, which is not a valid probability, right? So that's why your whatever operator, any addition, if you want to do, right? Whatever state you are getting, right? Suppose the amplitude is how much? The amplitude of the quantity 2 is 1, right? If I convert this 2 into some, say some some quantum state, for example, right? I cannot directly convert that way. So it should be a vector, it should be a vector somehow, right? And then the amplitude is one. The amplitude is one. You can add these two things in whatever way. You may get something which is more than one, which is not a quantum valid quantum state. So addition, simply addition is not a valid quantum operations. Any operation that is valid should be always a unitary matrix, right? So this is the explanation why you cannot do these things, right? Okay, sir. So somebody asks how quantum computing is useful in finance, right? Uh, Things will come slowly. You just need to be a little bit patient to understand the basics part. Once you understand, once I converted this entire physics to the computing part, then slowly I'll tell you how it is useful. Okay, I'm keeping this question in mind. Now, let us come back. So I am defining various terms. What is superpositions? Still, I haven't defined what is interference. I could define these things in simple way, but I'll come what is interference from probability lecture probably tomorrow. Okay, and today I'll also define something called entanglement, right? So let me define something called tensor product, and this is very important for why quantum computing is so much powerful, and this composite quantum system will give us answer. Okay. Yeah. So for a system, for our systems which comprise of multiple quantum system or multiple subsystems, then the overall quantum system is the tensor product of individual system, right? And the representation is this O times. This is the notation for tensor product. What it is saying, and I will explain how it works mathematically. Okay. What it is saying, suppose this is a quantum system one. This is psi one. This is one quantum system. It can be how you define the quantum system. Maybe this is certain artificial atom, right? And you created a quantum state. Suppose this is your ground state and this is your excited state. And you created a superposition state, right? Between Ket0 and Ket1, right? With at some equal probability between 0 and 1 or some probability in 0 and 1, right? Somebody asks, is it possible to buy everyone? No, it is not possible to buy a quantum computer by everyone. Okay, it is so costly now because you need to um, create cryogenic setup of supercomputer. So we need to wait for that those many years to have quantum computer. But everybody can use a quantum computer via cloud. Like you can use a quantum computer like IBM machine just by creating an account on the IBM platform, or there are other companies also they might offer access of quantum computer. So there is another question: what arithmetic operation does quantum computer? So quantum state is a vector. So any operation you want to do on the vector, that vector obeys any principles. Like for example, these kind of matrix operations on the vectors you can perform, right? Um, uh, can you share the quantum machine? Okay, I'll share all the links and everything. Okay, fine. So suppose you have a wave function psi1 or a quantum system psi1, and you have another quantum state, say state 0 and state 1, and this is some quantum state psi2, for example. This is psi1, right? And this is a system, this is a quantum system. So this is a electronic system 1, this is a fermionic system 2, right? And it can create a composite quantum system together. It is not the addition or multiplication. Composite system, composite quantum system. So we represent this as tensor product of psi1 and psi2. When you will be designing circuit, you will see you are starting with 2 qubit, and this is creating, if you take 2 qubit, it is automatically creating a, okay. Mathematically, let's try to understand how it works. So suppose mathematically, I'll take the all question. Just let me finish this part. I'll answer each and every questions. Don't worry. Okay. So suppose there are two matrices, tensor product. So tensor product. Right. So the tensor product of two matrices A and B. You can do tensor product of matrices, vectors, and tensors as well. So suppose A matrix has the element say A11, A12, A21, and A22, right? And B matrix has the element B11, B12, B21, and B22. This is A and B. Okay. And you will want to do the tensor product. So the answer will be A11 times the matrix B, A12 times the matrix B, A21 times the matrix B, and A22 times the matrix B. So this is the way how we do tensor product. So let us take an example with a vector, in fact, with a simple vector. Suppose V is, all vectors are in fact matrices, okay? And for example, if I take this matrix, so the first column is a column vector, right? The second is another column vector. This is a row vector. This is a row vector. So anything you learn for vectors will be useful in the matrices. Any properties that is working for the matrices will be useful for the vectors, right? So suppose let's take to example V equals to 1, 2, one vector, and W equals to 3, 4, another vector, right? And for basically if these are two quantum state, then this vector and this vector has to be normalized, okay? So it will be 1 by 1, 2 by 1 by square root 2, and it will be 3, 4 divided by 1 by square root 3 square plus 4 square, right? That's how we do the normalizations. Means state has to be normalized. But these are some ordinary vectors for now. And you want to do the tensor product of V and W, right? So it is 1, 2 tensor product with 3, 4. What we have learned, it is 1 times, you can say 1 times 3, 1 times 4, 2 times 3, and 2 times 4, right? It will be 3, 4, 6, 8. Now, individually, they are 2 cross 1 system, 2 cross 1 system. But now you have created 4 cross 1 system, right? So if you have a 2 cross 2 operators, quantum operators, so you can create 4 cross 4 quantum operators using the composite quantum behavior, right? So that's how if you take 3 qubits, say 0, 0, and 0, ket 0, and you create a quantum circuit, as a whole, it is creating 8 cross 1 composite quantum system. That's the power. So if you have n number of qubits, how many, what is the composite quantum state we can create? 2 to the power n composite quantum state we can create. Quantum state. And this is the dimension basically, 2 to the power n dimension. Okay. So this is one important thing that we need to know regarding the how we can create the entangled state. How we can create the composite quantum state, quantum system. Now I'll come to something very important that is called the entanglement, and that is related to the tensor product basically. I see there are questions, lot of questions, so I'll come. One question, sir, can we use quantum as a programming language like Java, Python? So you can use Python to code quantum like programs and all. In my notes, if you see, there are some of the example problems are also there in Python. Operators operate on states or qubit. So qubits are basically in mathematical form, they are quantum states. They represent quantum state, right? Of course, operators operate on the states. Okay. So now there are some more things. So suppose now there are In quantum mechanics, the state of a qubit, is represented by a vector, right? That we just learned, by a vector. Especially when we say qubit, it's a vector in a two-dimensional complex vector space. Right. So and the basis vectors that we have seen, basis vectors are either up state or the down state, Ket0, Ket1, right? Now, if you are using two qubits, right? So if you are using two qubits, so then we have four computational basis states: 0, 0, 0, 1, 1, 0, and 1, 1, right? For two qubits, the composite quantum system, there are four states. Now, these four states are, in fact, this is the tensor product of 0 and 0. You can break like this: 0, 1, 1, 0, and 1, 1. Right? Now, a general two qubit state can be written as general two qubit state. We can write as, say, general G equals to alpha times 0, 0 plus beta times 0, 1 plus gamma times 1, 0 plus delta times 1, 1. Right? Where alpha, beta, gamma should be gamma, and delta, these are complex quantities, complex numbers, right? And the quantum postulate says that the summation of alpha square plus beta square, alpha square plus beta square plus gamma square plus delta square equals to 1, right? Now we have to define two things. One is called the product state or separable state. Separable state, also it is called the product state. Product state is one that can be written as a tensor product of two single qubit states. So there is something called a separable state, which can represent, which is a separable state that can be written as a tensor product of two single qubit states, right? And that means that can be factored. Can be factored in the form psi equals to psi of A is for one system, tensor product with another system, single qubit system, psi of B, for example, right? Where psi of A is alpha times 0 plus beta times 1, and psi of B equals to, say, okay, already I have written alpha beta, so let me take some other values. Say A times 0 plus B times 1, and psi of B can be C times 0 plus D times 1, right? Now, if we expand this equation, if we put all these values, then what I will be getting, this psi equals to A times C00 plus A times T01. Just simply multiply this and this times this. So AC means this times this 00, right? A this time this 01 plus BC 10 plus BD11, right? So all the four states. Now, if we compare this with this equation, this psi general state, right? Then we'll be seeing that alpha equals to AC, beta equals to AD, gamma equals to BC, and delta equals to BD. You can compare this, and this with alpha, beta, gamma, and delta, right? And it then immediately it gives a relation that alpha times delta, this times this alpha times delta, which equals to beta times gamma, that is equals to A, B, C, D, right? If you can write this way, it implies the above expression, then this is the condition for separability. Condition for separability. So the states, any 2-qubit state, when you can represent any way, but ultimately it satisfies that alpha times delta equals to beta times gamma, this equation, then we say that this state is a simple product state. It can factored into simple 1-qubit quantum states, right? But let's take an example. Now let's take a composite quantum state. Composite state of 2 qubits. 2 qubits has some phi, it's some state, and the state is 1 by square root 2 0 0 plus 1 by square root 2 1 1. Suppose this is our some quantum state. Now you can ask me, is it a valid quantum state? Yes, it is a valid quantum state because 1 by square root 2 square plus 1 by square root 2 square, that is the sum of probabilities equals to 1. There is no issue. So this is a valid quantum state. But in this case, if we compare this equation with the above this equation versus this equation, if you compare, so you see AC and BD have some value, but AD and BC, right? These two are actually 0, in fact, right? So that means what? That means we are getting alpha equals to, here alpha equals to 1 by square root 2, beta equals to 0, gamma equals to 0, and delta equals to 1 by square root 2, right? So alpha times delta, that is equals to half. This times this equals to half, and beta times gamma equals to 0, right? So that means alpha times delta not equals to beta times gamma, right? So that means it is not obeying the rules alpha, delta, and beta, gamma. So we cannot factor this state. So hence the state phi cannot be factored, into tensor product of two single qubit states. This is called entanglement. This is called an entangled state. Okay, you have learned entanglement from physics with different experimental setup and all, but mathematically this is the way of defining entangled state. That an entangled state is one. Now let me connect it to the physics again, like how it is happening, right? In fact, this is called a Bell state. This particular example is called a Bell state, here also known as Bell state. Okay. So Okay, let me explain this part with a very simple example. Okay, suppose you take 2 qubit, QT-00 and QT-00, right? And you apply a Hadamard gate. I still haven't said what is Hadamard gate. Okay, I'll come. So what I have said, the state here, the this is a quantum state 0, this is a quantum state 0. What is the overall state? Overall state is 0, tensor product with 0. This is what we have learned, right? What is the purpose of Hadamard gate? Hadamard gate does the quantum superposition. It does the quantum superposition. It's basically a matrix, and this H matrix looks like 1 by square root 2, 1, 1, 1 minus 1. Okay. Now, if you apply H to QT-00, H matrix on the first qubit QT-00, what we are getting? 1 by square root 2, 1, 1, 1 minus 1 times 0. QT-00 is what? QT-00 is 1, 0, right? Now, if we multiply this vector times this matrix, what you'll be getting ultimately? You'll be getting a state. You can keep it as 1 by square root 2, and you can calculate these things. You'll be getting QT-00 plus QT-1. This state. This is also known as plus state. Okay. So it's just simple multiplication, just matrix time vector multiplication. I can just simply do it right now. So you can see matrix type. So it's like 1 times 1 is 1, 1 times 0 is 0. So it is 1, right? And 1 times 1 is 1, and 0 minus 1 times 0 is 0. So 1. So this is basically equals to 1 by square root 2. This particular state you can write it as 1, 0, right? 1, 0 plus 0, 1, right? These two. So this is what? This is your QT-00 and this is your QT-1, right? So this is a superposition state, 1, 1, equal superposition with half probability, right? So if you apply the Hadamard here, what we'll get? At the output of the Hadamard, we get 0 plus 1 state. That's why we call it as a superposition state of, we started with 0, but we are now a state which is a superposition of 0 and 1, right? With probability half. 1 by square root 2 means the square of this is half of probability, right? Equal superpositions. Now you apply a controlled X gate, that is called a CX gate, controlled X gate. So what it does, let's now play with this. Now once you apply the CX gate, so before the CX, what is my quantum state? This is my quantum state. Now I am applying CX. I'm removing this 1 by square root thing just for simplicity. Okay, let's keep it here. And we are applying CX on the state. Now see, here we are, this is the state here, right? Because we applied the Hadamard on the first qubit. But on top of it, there is a second qubit which is vacated, like it is a tensor product with this state. So what is the state? Then 0, 0. Tensor product with 0. This is my state because this 0 has to be tensor product with this. So this is equal to 1 by square root 2 Cx. And this state will be 0, 0 plus 1, 0, right? This is my state after tensor product. Now what this control X gate does is that it does nothing to the state 0, 0. So that means 0, 0 remains as 0, 0, but it operates on where there is first qubit is 1. Then if the first qubit is 1, the second qubit, it swapped to 1. This is the purpose of the control NOT gate, C NOT gate. This is known as the entangled gate in quantum. So Cx, when the first qubit is 0, it does nothing to the second qubit, but when the first qubit is 1, it swaps the second qubit. So that means if you apply Cx on the first qubit, you will be getting the second qubit also 1, right? And this is exactly the state phi. And this is the quantum circuit for this. Just what is the circuit? Circuit is very simple. A Hadamard and a controlled NOT, Cx. So we started with 0, 0, but we ended up with a state phi, which is a combination of 0, 0 and 1, 1 with equal probability, right? So here is the probability part, right? So you can see that if you want to perform any measurement on this 0, here you of course know what is the probability of the other 0. If you want to measure on this 1, you of course know the probability of the other one. That means this mathematical demonstration shows that the correlation within the entangled state are more complex than the simple classical correlation. This state of one qubit cannot be described independently of the other. You see, 0, 0, 1, 1. There is no intermediate state, 0, 1 or 1, 0. These state are not here, right? Only these two. That means if you want to do any performance on this is impacted, right? So that's why the state of one qubit cannot be described independently of the other. They form a single inseparable quantum system, and that particular system is called the entangled state. Right? Also known as the Bell state for the 2-qubit circuit. But you can create multiple entangled state as well. So that is the other thing. Right? So we covered what is tensor product and the performance of the C0 gate, how it works, the matrix forms, all details are in the PPT. I shared the note, no need to worry how it works, how it is different from classical XOR gate. That is also there. Okay. Okay, how the composite system things works. Okay, so in quantum, basically, there are certain things. One is called the state, like the vectors I was saying, like Ket0, Ket1, all these computational basis things. Matrices has to be unitary, right? So unitary matrix, like for example, the Hadamard gate, I just showed the example. Let me show you some more examples in the setting. Okay, this is the thing I just showed you, like any quantum state that can be represented as a superposition of the computational basis 0 and 1, right? 0 and 1. And if you want to measure which state it is, you just need to do inner product between the state and the computational basis, right? Now, there are various operators like Pauli X, Pauli Y, Pauli Z, right? These are unitary matrices. Say, for example, what is the purpose of this? Suppose you have a quantum state here on the blosphere. So when there will be programming class, it will be more easier. And suppose you want to do any operation on here, like you want to rotate this quantum state to this part, right? Or this part. So you need various metrics that has to operate on the on the quantum state psi. If you want to rotate around x-axis, around y-axis, or around z-axis, so there are matrices, Pauli matrices such as 0, 1, 1, 0. It does 90-degree counter clockwise rotation of the quantum state. This is called the Pauli X gate. There is 0, minus I 0. This is called the sigma y operator or Pauli y operator. There is sigma z operator. It does the rotation around z axis. So 1, minus 1, 0, 0, right? So in the qubit space. And okay, before going for some examples, let me check if I can give you some more examples of the quantum gates and all. Right. Okay. So let me take 5 minutes maximum just to cover the what is qubit and all again, right? So I am removing all physics and everything now. And now just what is quantum computing for those who just totally wants to avoid physics part and everything, right? Just give me 5 minutes. Okay. The basic unit of quantum information right now you have a vector quantity, Ket0 and Ket1. And all the quantum informations that right now you will be using are vector quantities, right? Vector quantities. Now, when I say vector quantities, the most important part of vector is the basis of the vector, where and how the vector is represented in the space. So you need, like when you try to build a building, right? You need to basically form the base of the building, right? Somewhere. So the base or the basis of the quantum information are these Ket0 and Ket1, right? They are the fundamental unit of quantum information. In fact, they are simply like the coordinate system x and y, Ket y. Like any vector you want to represent, you need some coordinate system, orthonormal basis, right? Ket0 and Ket1, they are orthonormal basis in algebra. In physics and chemistry, they are some energy state like the ground state or the excited state or the electronic spin like the positive spin, like counterclockwise spin or the clockwise spin. In ion trap technology, they have certain particular ions, right? That is specifying the Ket0, Ket1. So various technology, how they define Ket and Ket0, Ket1 different, but mathematically they are vector quantities. Now, so this is classically your representation of 0 was something like this, right? Classically, you are representing your information like 1, but because it is a vector quantity, so I gave a vector notation here, vector notation here. And in superposition, you have both the state Ket0 and Ket1 because you have half of the probability 1 by square root 2. So if you apply Hadamard gate, you get you basically get to see this kind of state, both 0 and 1. Just I applied, right? So this is the state of applying Hadamard gate, say applying Hadamard gate from here to here, right? And if you have more number of basis states, so you can create with 4 bits, right? You can create 2 to the power 4 quantum basis states, basically like this, right? And the purpose of the quantum algorithms is to do interference and entanglement, especially wherever it is required. So the purpose of superposition is to create multiple basis states. Purpose of interference is to basically work on the probabilities, right? Interfere with the probabilities of various basis states and yield the probability maximum, which is required for your solution states. Whatever bases are important for your solution, it maximizes the probability using quantum interference, right? So that is the part. Now, simply you have your quantum state is just a vector. So what you want to do, you want to operate on the vector in order to do some operation. So if it is on the complex plane, so for example, you want to rotate this vector from here to here with theta angle. What do you need to do? You just need to multiply a rotation matrix with this vector, like cos theta minus sin theta cos theta. If it is a 90-degree angle, like 0, 1, 1, 0. So basically, if you start with the Ket state 0, right? And if you basically apply 0, 1, 1, 0, right? So 0, 1, 1, 0 operated on 0, 1, that is Ket1, right? So basically, if you multiply these things, 0 times 0 is 0, 1 times 1 is 1, so 1, and 1 times 0 and 0 times 0 is 0, so 1, 0, that is equals to state 0, right? So you are applying a gate, quantum gate, right, on a quantum state Ket1, and you are getting Ket0. Similarly, if you apply same matrix on the Ket0, you will be getting Ket1. This is called the NOT gate in quantum computing. NOT gate in quantum computing. This is your also known as the Pauli X operator. Okay, this is simply a rotation matrix, right? You can see it's a rotation matrix. It's a rotation matrix. It's the Pauli gate. It's the NOT gate in quantum computing. Okay. Similarly, there are other gates. Like for example, let's start. There are various types of gates. So one set of gates we called as SU2 gate, super unitary 2 number of gates. So they have mathematical definition why we call so. I'm not going that direction, but in general, Pauli X, Pauli Y. So don't always try to pick up your knowledge from classical computing and fetch here, because this is a very different technology. The operations are very different, because classically you were doing all the Boolean logic. Here you will be doing all the linear algebra, matrix, vector multiplication, matrix multiplications, and all that we learned from the linear algebra case. And all our gates are basically unitary matrix. Because if you multiply, simply take any gate, say for example, x star x, what you will be getting? 0, 1, 1, 0 times 0, 1, 1, 0. If you multiply these two matrices, you can easily check it is 1, 1, 0, 0, identity matrix. Any matrix you choose, that has to be unitary matrix in order to obey the probability or the quantum postulates of quantum mechanics, right? So there are some more gates like Hadamard gate. It does the quantum superpositions basically. So if you have a 0 state, it can prepare plus state. Plus state means 0 plus 1 by square root 2. If you have one state, if you apply Hadamard, you will be getting minus state. That means 0 minus Ket1 by square root 2. There is T gate, phase gate. So some of the gates are known as Clifford gates. Some of the gates are known as non-Clifford gates. So there is more literature on that. I'm not covering those parts. Now these all are acting on the single qubit. Why? Because the dimension is 2 cross 2, right? And for a single qubit, the dimension is 2 cross 1. Now we, from our childhood knowledge, we know that matrix and vector will be multiplied if the number of column equals to the number of row here, right? So 2 cross 1 state, we need to have 2 cross 2 operators. So these are all SU2 operators. Similarly, if you have a 2 qubit state, right? So you have 2 qubits means you have 4 cross 1 is the basis state dimension, right? For the like 0, 0, 0, 1, 1, 0, 1, 1, they all have 4 cross 1 dimensions, right? So a quantum state represented in 2 qubit system has a 4 cross 1 dimension. So you need 4 cross 4 matrices to operate on them. And one of the prominent gate there is the C0 gate, which is called the entangled gate, because entanglement will work only if there are 2 quantum systems, right? 2 quantum systems. So if there are 2 quantum systems, you can check whether they are entangled or not, or you can prepare entanglement using this kind of gate, C0 gate. There is swap operation. So if there is a one information in one quantum system, another information in another quantum system, if you apply this particular gate, so basically this information will go here, this information will come here, right? This is the purpose of this swap gate. So these are some of the logic things. So we'll continue again tomorrow. And if you have any question, please feel free to ask me. Okay, so I can see some questions. So let me pick 1 or 2 questions today. One is, it may be asking basic question. All questions are good. Don't worry. Feel free to ask question. Why quantum state is represented in dimensional space? Why not 3 or 4 dimension? Why are you restricted to 3 or 4 dimensions? Okay. Mathematics says there are like infinite dimensions, right? All the how we define that. Okay, maybe tomorrow if I get some time, I'll talk about dimensions. Okay, so basically, more dimensions you can create, you can basically represent your information like more efficiently. Basically, you can speed up certain things, right? The more space means you can solve a problem with more efficient way, right? IBM provides a mean for quantum computing, but if I try to use Qiskit from IBM, it is showing me pricing. I tried using VS Code, Google Colab, running it, but using it, we are able to 30 qubits beyond. Okay, if you want to use hardware, I don't know the current situation, but till last month, it was totally free. But I believe it is free till now also, but maybe there might be some more information required. I'll get back to Professor Pillai, sir. Okay, CX and C0 are the same. Yes, CX and C0 are the same. Feeling too hard. Okay, if you are feeling too hard, I'll try how I can address these things. It's good to be understood. Nice. Okay, thanks. Maybe any. Okay, maybe later you can say.
Yeah.
So
Thank you.
I believe that some of the scholars might feel actually a bit difficult because otherwise the way, even if I go with like only on the simplified or the surface things, other people will not feel good. That is also there. So I'll try to combine both the pictures. Yeah.
Yeah. Actually, there is a little bit of homework that we will need to do. As I mentioned, I've shared in the group also QT-01 link we have shared. And if you could look up some more basics you would like to look at. So actually, we have not yet started quantum. When we come to quantum technology and applications, we are going to start. But Mustafizur sir has taken some extra effort. He has spared some of his own valuable time, which he can actually start off and teach linear algebra, but then he has paid that time so that you get a basics. And actually, quantum, please understand that you take some time to digest and do it. That's why we are doing only 2 hours a day. Just imagine if we taught 8 hours from morning to evening, there's no problem. We can have 4 speakers, they will teach 8 hours. But we will not be able to digest and understand, and hence we have put only 2 hours. Now, this 2 hours is also not sufficient because you are listening for the first time. So, what you need to do is you please go back, and whenever you are having instead of watching reels and wasting your time on useless stuff, please focus on this. You can quickly skim through because some of the concepts you can skip through. Some of the concept which sir has explained, now you go through in detail, right? And then make your own notes, right? Please note, please write your notes. My student is sitting behind and they're making notes of everything. So she's writing all the pages, like 4 or 5 pages every day she's writing. So please understand that you will have to do that, right? Those who know, like people who are from physics background, electronics background, and who are good in mathematics, right? They will very easily understand what sir has told, and they will
even
enjoy it.
sir, I mean, I repeat the same thing. It's the last 2 3 years I'm teaching everywhere, like SN Bose, IT Daily, MNIT. But every time still I prepare notes whenever I go to the lectures because I feel the audience might be different, the people might be different, the way might be different, and it is not needed to remember everything in mind or always following notes. So I mean, I feel also good to write things. Thank you.
Yeah, please write notes. Please prepare your notes. Wonderful material. Actually, we are giving slides, but you will never open the slides. Let me give you guarantee. Only for writing the quiz you will open, right? Because so many slides, some 50, 20, 25 slides every day, sir will share, right? Every resource person has shared the material, notes, everything they've given free of cost. He has now shared his link. So you will find a lot of notes, material, videos. Wherever he has delivered the lectures, all those links are there. So you can go through some of the lectures. Material is unlimited and knowledge is free. Only thing is we need to put the time. I think what Mustafizur sir was mentioning about IBM is going to give you quantum resources for 10 minutes every day, which is free, right? If you
I
want,
think for beginners, sir, sorry to
yeah,
interrupt you, sir.
right,
For
yeah, please go ahead.
beginners, hardware is not needed. You start with SARC, Google SARC, or Amazon, whatever device you are getting. Just use simulator and understand what computing means. Solve basic problems like toy problem, also like simple Simon's algorithm or whatever it will be taught in this course. Just do that. When you will be doing research and you need valuable research for publication, patents, those things, then only you go for the hardware access because hardware means somebody is spending money, whether you, whether IBM, whether government, right? But there are lots of simulator. Initially, you can start because these are initial courses. You can go for any quantum simulator device by any company and just practice there. Whether it is Qiskit, Pennylen, whatever it is, just do practice whatever it is required. Yeah, sir.
Yeah,
Please, sorry to
and
disturb.
any content that you look at, like you take it, Qiskit is open source. You take Pennylane is open source. You take Q inverse open source. You take QSIM, it is open source, right? So you can open source means freely available, and at least you are able to do what you want to do, right? So there is absolutely no problem in getting the things done. So that's what please try to understand. So some of the basic things you may not need, but of course it is not free. There is no free lunch when you want to do some real HPC kind of applications where huge problems you want to solve, obviously it will be costly. IBM will give resources, I will give concessions, but definitely they will charge. Please try to understand that because they are also spending, as Mustafizur sir mentions, somebody is paying the cost. So whether it is electricity or whether it is anything that is there, and the resources and funding also to provide for research and such training programs and making people available to train us. You just understand that IBM is also spending resources, right? So hence we can come to a conclusion. And you don't know the value of Dr. Mustafizur's time. He is being very gracious in answering so many doubts and queries. And IBM has sponsored that he will be available for us and teach this lecture. So I am sure you are understanding his experience with IIT Kharagpur and the learning process there. And he has a passion for teaching. So that's what we are enjoying. So let's meet tomorrow again. I think tomorrow we will stick to the syllabus and
Yes, yes.
sir will take you through the linear algebra and the probability and statistics. And hopefully, as Richa madam and others take you through various
Right.
parts of the course, the basics will be covered. And then we will go to QT-01, which will actually introduce you to the quantum topics. Then you will understand words like entanglement, superposition, what do you call measurement, and many other concepts like this, the Dirac notation and all that. So let's hope, and we will meet Mustafizur sir tomorrow at 3 o'clock. So
Yeah,
all those
sure.
who have issues with the again, the group will be opened, and if there are any questions, please let us take it.
Right.
Canvas will park for some time. Don't worry about Canvas. Worry about WebEx. If you are registered on WebEx, if you are logging and viewing the lectures on WebEx, you have done a great job. Thank you so much for joining. If you have any doubts, the group will be open again, so you can post your questions and queries, right? As of now, let me tell you, there are 1120 participants which are registered in this course. About 600 of us are joined here. So hopefully we should touch around 1000. We should reach somewhere around 900, 950 every day. So let's hope and wish you all the best. Tomorrow, 3 o'clock, we'll be back again. For those who are having issues, please write to us. We will try to sort out as much as possible today. And hopefully from tomorrow onwards, all of us should be on the thing, right? We are going to send a mail for your registration also. you will get your login ID and password from MNIT's portal. You will have access only to register for one course, and a later date we will go. If you want other courses, we will open it for you as well. But as of now, not to confuse you, you will get only access to one course. Register for that course, pay ₹500, and complete the registration process. Thank you so much. Thank you, sir. Thank you, Dr. Mustafizur Rahman. Thank you, Anil, sir. And
Thank you, sir. Thank you very much.
Thank you, sir.